Hello, everyone. Mr. Minnick's my name, math is my game. And today I'm joined by my fourth period statistics class. We will be introducing what's called normally, as opposed to not normal, normally distributed variables. Chapter 6, we're delving into some new territory here. And the interesting thing is, even though it's a new chapter, we've already talked about variables. We've already talked about things related to normally distributed variables. So really there's not much new, even though it's a new chapter, a new section. So the first thing we need to do is define a density curve. And by definition, it's simply a distribution that has a smooth curve. It's a distribution with a smooth curve. I don't know if any of you are planning on taking a calculus class, but if you take calculus, you really study curves quite a bit. And in fact, you study lines, tangent to curves, and that kind of thing. But in the context of what we're talking about in statistics, and I'll have bigger pictures here in a minute, in earlier sections we made these things. What are these things called, where we have these little lines like this that kind of say how much of something there is? Anybody remember what those are called? The histogram, right? Or a frequency distribution. Okay. So what they do with those is they try to approximate it with some kind of curve. And they try their best to get a smooth curve, and it's not always going to be exact. And some parts of the box are under and some parts are on the outside, but they try to approximate them. So here's a couple images that I found on Google. Got to remember that second O. So if you notice this first image here, there are certain spots of that image where the bars aren't even under the curve. Like there's a clear void where there's no bars under the curve. But what they try to do is get as much under the curve as is outside of the curve. Okay, so when we talk about these smooth curves, this is the kind of thing we're talking about. How's everybody doing so far? Make sense? So a density curve is simply a distribution with a smooth curve. Okay. So from this point forward, when we talk about a density curve, we're just talking about a frequency distribution that has some kind of curve going around it. Okay. Ready? Good. Here we go. So there's basically 2 or 3 key facts in this section. And there's 2 properties of density curves. The first is this. And this kind of goes back to pre-algebra concepts. A density curve is always going to be on or above the horizontal axis. I know I'm guilty of this sometimes. Whenever I sketch this frequency distribution like that, I forget that in the context of things, that's really occurring in a Cartesian plane. So what I'm saying is, if you think about your x and y axis, the x-axis is this horizontal axis that they're talking about. So when we talk about this density curve, you know, what we're really kind of looking at is the fact that that curve is going to be either on or above that axis. Okay, so that's the first of 2 properties of density curves. The curve itself is going to be on or above the horizontal axis. If it were merely above, let's think back to our Algebra 2 days and maybe pre-calculus days. If that curve were strictly above the horizontal axis, that horizontal axis would serve as what? A three-syllable word that starts with A. An asymptote, right? But the fact that it can be on it, it's not an asymptote. But anyway, that's another story. So the second property here then is this. The total area under a density curve equals 1. And in parentheses, they said, and above the horizontal axis. Well, we already said that the curve is above the axis, but the total area under a curve and above the horizontal axis equals 1. So the part in parentheses, if they didn't have that, we'd kind of have a contradictory type situation. If you could imagine having this horizontal axis and having a curve that was on the axis, and we would say, okay, what's the area under that curve? Well, there wouldn't be any area, so that's why they mention about it having to be above the axis too. Okay, so what they're really saying here then is if this curve looks like this, and you were to find the area in there, that the area there is equal to 1. Okay. Now from studying probability, we also know that the probability of a certain event is equal to 1, right? So the fact that the area is a 1 is basically telling us that if we were to take slices out of this, that individual slices are going to correspond to probabilities. Okay, so that's what we're going to be getting into with this. So these two properties of density curves, the authors of your textbook call this key fact 1 from this section. Okay. Any questions about anything up to this point? Or comments? Or concerns? Or short debates? Long debates? Medium debates? Any shout outs? Ethan Milko. Fratley Martin? I'm not sure what that's about, but okay. All right. Dur Martin? Okay. All right. All right. So here comes key fact number 2. Key fact number 2 is that for a variable with a density curve, for some variable with a density curve, and I had to read this about 6 times to understand what they were saying, and I tried my best to highlight what the point of this is. For a variable with a density curve, the percentage of all observations of the variable that lie within any specified range equals, at least approximately, the corresponding area under the density curve expressed as a percentage. Say that again. Give you a few minutes to write that down. So we're talking about a variable, something that changes from one person to the next. We would come up with a frequency distribution of it, and consequently then have a density curve. Key fact 1 said the total area under the curve but above that horizontal axis equals 1. And this key fact 2, what this is telling us is that suppose we're talking about, I'm trying to think of a variable. Suppose we're talking about the temperature of something, okay? The temperature of something. And on a particular interval here, we have the temperature 62 degrees, and it goes up to under 63 degrees, okay? So suppose that the area in that particular block, in that particular chunk, suppose that that area equaled something like, 0.093, okay? What we're saying is 9.3% of all the observed temperatures are in that interval. It's nothing super profound. takes a minute to think about it, but what we're saying is whatever the size of that area is in terms of square units, that's the percentage of observations in the whole population that are in there. Okay. So again, it kind of goes back to this. The total area is 1, total probability is 1. So what we're in effect saying is the amount of things inside one of these blocks is really a probability. Does that make sense? Kind of, a little bit. So I think at this point it would be prudent to go on the line to Math Excel. So I'm going to go ahead and sign into Math Excel, and we'll take a look and see how difficult some of these might be. If you have your Chromebook charged, LOL, RO. How do you say rolling on the floor, laughing? RO, whatever that is. I'm laughing because do the Chromebooks charge that well? I shouldn't say anything about that. Anyway, so if you have your laptop charged up, ready to go, and you'd like to fire it up and work along, you're welcome to. So here we are with this 6.1. When you see how easy some of this stuff is, you're gonna say, really? That's it? So question 1, the total area under the graph of the equation over all the possible values of a random variable must, before we even see anything in the drop-down box, I'm thinking it's going to equal 1, right? Must equal 1. Let's try that. The height of the graph of the equation must be, oh, that's interesting. Less than 1? Well, possibly less than 1, but the fact that it's got to be above the horizontal axis tells us it's got to be positive or greater than 0, right? So I'm thinking greater than, between 0 and 1 inclusive, greater than or equal to 0, or less than or equal to 1. Let's try this between 0 and 1 inclusive, see what happens. The area under a graph represents a probability. Since a probability must be between 0 and 1 inclusive, consider how this affects possible values for the height of the graph and the total area. I think we're okay with number 1. But I think number 2 we got to change. Greater than or equal to 0, let's try that one. There we go. There we go. So far so good. All right. Moving on to the next one. Fill in the blank. It's the percentage of all possible observations of the variable that lie to the right of 11. Where are they getting 11? Equals the area under its density curve to the right of something. So what they're saying here is you've got this curve. Here's this horizontal axis. Here's number 11 somewhere. And they're saying the percentage of all possible observations of the variable that lie to the right of 11. So they're saying the percent of all the things in here equals the area under the density curve to the right of what? 11. It's going to be to the right of 11. Wow. It's a silly question. They want you to understand the fact that areas equal percentages. Areas equal percentages. That's the point here. Okay. Assume that the value under consideration has a density curve. The area under the curve that lies to the right of 14 is 0.435. What percentage of all possible observations of the variable exceed 14? So basically all they're asking us here is to change this area, which is a decimal, to a percent. So it'd be 43.5. 43.5. There it is. Now they're saying, okay, all the ones to the right of 14, there's 43.5% of them. How much is on the other side? Now we got to use the complement here, right? Because the total area is 1 or 100%. So we're just going to subtract from 100% this 43.5. So how much is that going to leave? Somebody said it. 50, is it 56? 56.5? Okay. So far, so good? Piece of cake? Makes sense? Okay. Let's move on to number 4. Number 4 says 29.9% are less than 16. What's the area to the left of 16? So same thing. We're just going to change that percent to a decimal. 0.299. There we go. Part B, again, we use the idea of the complement. How much is on the other side? Or how much is left out of 1 if we already took up 0.299? 0.701. God. Well, this isn't so bad, is it? Okay. Moving on to number 5. A curve has area 0.622 to the left and 0.378 to the right. Could this be a density curve? So the question we should be asking is, it's a density curve if the total area equals 1. So what we're asking is 0.622 plus 0.378. Is that equal to 1? If it is, then it is a density curve. If it's not, then it's not. So does that add up to equal 1? It actually does. So the curve could be a density curve because the total area is equal to 1. Okay. Your particular problem, the numbers might not add up to 1. Everybody good with that? Matter of fact, let's try another one. Let's try another one. 0.637 and 0.366. Do those add up to 1? I think those actually do too. There's got to be one where it doesn't. Do those add up to 1? Oh, wait a minute. Do those really add up to 1? So on this one, we're going to say it could not be a density curve because the total area is less than 1. Okay? All right. Cool. So number 6 we haven't got to yet. So let's go back to the notes and see what else we got to talk about. Next thing we got to talk about is Spanish. Mrs. Bell. No, bell shape. I'm sorry. We got to talk about normal curves and bell shapes. Bell shapes. I'm pretty sure we've mentioned this, haven't we? We didn't call them bell, or maybe we did call them bell shapes. Or we did call them normal shapes. Anyway, a normal curve or a bell curve, by design, it says the shape for the distribution, it's usual. The normal curve, the bell-shaped curve, the shape of the distribution is usual. It seems weird. Maybe we're going to have to explore this a little bit further. Let's see if we could think of some variables where in the universe, in the world, in a population, things fall into a certain type of distribution. In other words, if we were to make a frequency distribution, the graph of it is going to kind of look something like this, where there's not a whole lot of deviation from that shape. In other words, where the middle is the middle and there's as many people below the middle as there are above the middle. And there aren't these random populations of people who are much greater than or much less than, or things about these people that are much greater than or much less than. So let's think about income. Anybody ever see that video about the distribution of wealth in America? The top 1% of Americans' wealth is greater than that of the lowest 90%. Would that be normal shaped? I don't think so. Let's think about potholes. Let's think about potholes along the lines of latitude. Do you think that would be normally distributed? If you consider America and kind of go from the middle of America and look at how many potholes there are? Or do you think there's going to be more potholes in the north than there are in the south? Probably going to be more potholes in the north, right? Because we have the cold weather and the cold when the water gets in there to expand. Yeah. So that probably wouldn't be normally distributed. But what would be? What's something where there are as many people above average as there are below average? What's a variable that we could talk about with people? Grades in school? They try to do that with that one thing that you take every 6 months to try to get a good grade, to try to get scholarship money, to get money to go to college and to go to college, to get entered into college. The ACT score. Yeah, an ACT score is actually like this. What else is like this? Heights, absolutely. ACT score is one. Height is another one. There are as many, in general, there are as many people above the average height as there are below the average height. So ACT scores and heights fall into this category. So this next bit, there's a lot of writing here, and I'm not going to ask you to write it all. I just want you to maybe jot down the highlighted words here. And this is the part of stats class where, honestly, I left class. I went and got a cup of coffee at Starbucks when I was in stats class. Because stats teachers like to throw these words around. They say it's normally distributed. If something's close to being that, they say a normal distribution approximates it. So if you have a frequency distribution that looks something like this, they would say that's approximately normally distributed. Even though a normal curve doesn't approximate it the best, it is approximately normally distributed. Okay, so it's now just the words in bold. I would just kind of jot those down. The population is normally distributed. The population is approximately normally distributed. Okay, that just means that the frequency distribution, if you put a bell curve around it, it would roughly approximate it. It would work. Okay. What do they say about April showers? It's going to snow tomorrow. Thanks, Obama. It's not his fault. I'm going to say, let's go snow machine. I'm hoping for one more snow day. Let's go snow machine. Okay, so again with the language, anytime they say normally distributed or approximately normally distributed, they just mean if you have a frequency distribution that's pretty close and a bell curve might kind of come close, then to simplify some calculations or some ideas, we say it's approximately normally distributed. Okay. Doing all right? So I guess we'll go back to Math Excel and see if we picked up anything that'll help us yet. Question 6. A variable is approximately normally distributed. If you draw a histogram, roughly what shape will it have? Roughly bell-shaped. There we go. roughly bell-shaped. We doing all right so far? Okay. Number 7. Ooh. We got to talk about some more stuff before we can answer this one. Okay. So to answer this one, here we go. This would make a great compare and contrast essay quiz question in the future. Maybe next week sometime. The shape of a curve, when I talk about the curve, I'm talking about the normal curve from this point forward, unless otherwise noted. The shape of the normal curve is determined by the standard deviation. What I mean by that is curves, different curves are going to look different. Use a couple different colors here. Some curves are going to be really tall and skinny, like that. And they will touch down. They will actually touch down. Remember, it's not necessarily an asymptotal type situation. They will actually touch down on the horizontal axis. Another curve might seem to be an average height and width, like that. And again, they will touch down, so they do kind of terminate there and there, and this one might terminate here and here. Okay. And others still might be very widespread, like that, over the whole entire curve. And I never understood this until I thought about it. Think about the definition of a standard deviation. Think about the definition of a standard deviation. By definition, standard deviation is defined as the measure of that 6-letter word. What 6-letter word? It's a measure of, not a measure of center, but it's a measure of, it says on average, one item differs from the average by this much. So it tells us how far something is apart or spread out. So it's a measure of spread. So let's think about this. In the event of this red graph here, is the data spread apart very far? No. So in the case of the red one, we would expect that to have a small standard deviation. Now let's use the variable. What variable goes with standard deviation? Sigma. Good. So we would expect that to have the smallest sigma. For the green curve here, that one is spread out the most. So we would expect that one to have the largest standard deviation. Okay. So that one's going to have the largest standard deviation. Okay. Does that make does the logic of that make sense? Now the interesting thing is that some curves, this red curve, it could actually show up over here, it could show up over here, it could show up anywhere along the horizontal axis. Well, just about anywhere. Got to be real careful how I say that, but there's an infinite number of places where it could show up. But where it shows up is contingent on the mean. The mean determines where on the horizontal axis the curve shows up. So suppose we have a distribution where the standard deviation is something like 3. We might have a curve like that. Let me go ahead and clone that. Oh, what did I just do? There we go. We'll have another one with the same standard deviation of 3. We'll have this one over here. And we'll have still a third one. And this one will also have a standard deviation of 3. Okay. So notice they're all the same height, they're all the same width, but they're in different places. So the deal is, along this horizontal axis, This horizontal axis is kind of like our x-axis. It's really a number line. I don't know if you know that. The horizontal axis is really a number line. So there might be a number 0 here. There might be a number -1 here. There might be a number, actually that wouldn't be -1. It might be like -5 or something. And this might be +5. So if the blue one has a mean of 0, it would be located right there. If the red one had a mean of 5, it would be located right there. And if the green one had a mean of -5, then it would be located right there. Does that make a little bit of sense? Now, one of these is special. One of these is abbreviation, is what you don't want to get. I shouldn't say that. We talked about this in an earlier chapter. The blue one's a standardized normal distribution. When you standardize it, I don't know if you remember this, a standard normal distribution has a mean of 0 and a standard deviation of 1. Remember talking about that a while ago? Okay. So the standard normal distribution has a mean of 0 and a standard deviation of 1. And this is actually a picture of the standardized normal curve. Okay. So I'll leave that up there for a minute. You probably want to put that in your notebook. Again, if there's an upcoming quiz over 6.1, this would be a good item. What's the mean and standard deviation and sketch of a standard normal curve look like? So standard normal distribution, or the standard normal curve, the mean is 0, standard deviation is 1. A long time ago when we talked about outliers, I don't know if you remember that one outlier test, we said if you look at an upper limit of the average and you add 3 standard deviations to it, anything above that's an outlier. And there is a little bit of room under the curve out on that end. There's very minute amount, but anything out there is an outlier. Similarly, anything down here is also an outlier if we go 3 standard deviations below the mean. That was one of those tests that we used a while back. And in a future section, we're actually going to find out just how much is down there or up there. And it's not much. It's actually less than 1%. It's actually less than 0.5%. So. We doing all right so far? We're almost done with this. We're going to look at one example. We mentioned before that heights are normally distributed. We're going to look at an example with heights in it. Kind of just talk one more time about how those are percentages. And that's about it. Okay. So this example has 3,264 college female students that were measured for their height. It's got to be a pretty big college. That's a lot of students. 3,264 female college students were measured. It doesn't say anything about their age, but their heights were measured, and they found the mean average to be 64.4 with a standard deviation of 2.4. And I didn't put the whole table in there. But what would end up happening if you did take the whole table and you were to make a sketch of it is you would have something that would look like that would fit what we think of, and I can't sketch a normal curve very well, but it would fit what we think of as the normal curve. Okay. So again, just to kind of reiterate what happens over here, let me choose a different color here to choose this blue one. Over here, if we had this interval from 67 to less than 68, the area of that block, if we think about the geometric area, the area would be 0.0735. And what that means is that 7.35% of the females studied in this lie in that interval as far as their height is concerned. Okay, there's 7.35% who are between 67 and 68 inches tall. What would the total area under that curve be? It would be 1, and it actually is. Okay. General ideas of this make sense overall? Okay. So we're going to go back to the homework. There's one question that we won't be able to answer, and we'll have to look at one more formula for that. So let's see. With the normal distribution, which has a wider spread, the normal distribution with mean what has a wider spread? Mean 3 and standard deviation of 4, or mean 4 and standard deviation of 3? Here we're looking for the one with the bigger standard deviation, so it's going to be the one with the mean of 3 and the standard deviation of 4. There we go. Let's try another one like that. Which one's going to have the wider spread? The 9 and the 8, or the 8 and the 9? The 8 and the 9. Remember, we're looking for the one with the bigger standard deviation. Okay? Moving on to number 8. Which is correct? The mean of a normal distribution has no effect on its shape. Is that true, or is that false? That's false. What did the mean do, though? The mean did do something with the graph. It changes its location along the horizontal axis, okay? But it doesn't affect its shape. So to be real clear, when we talked about these two things, to be real clear, the mean doesn't affect the shape, but it does affect the location, okay? So this question is asking, does the mean affect the shape? No, the mean doesn't affect the shape, but it does change its location, okay? So I think we're okay on that one. Question number 9. Ooh, sketch the normal distribution whose mean is 5 and whose standard deviation is 4. It's either going to be B or C. You think it's B? Now, what they're doing is they're putting the mean in the middle, so it's not going to be A, right? And they're going out 2 standard deviations and then 3 standard deviations. So if we go out 2 standard deviations, the standard deviation is 4. Yeah, the B, I think it's B too. Let's try B. There it is. Good. Okay. So what they're doing at this point right here is they're going mu plus 2 standard deviations on that one. Okay. So let's take a look at number 10, and there's going to be one of these that we're going to run into that might give us fits. The area under a particular normal curve between 7 and 11 is blah, 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 blah. What percent lie between 7 and 11? Here again, change the area to a decimal or to a percent. So 83.4. Okay. The next one. I was wondering whose phone was ringing. It was my phone ringing. Shorter than 65. Oh, man. What are we going to have to do here? Oh, so the first part, let's see. Part A, the area under the normal curve, blah, 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 blah. That lies to the left of 65 is this. So here we're just going to change that to a percent, right? There we go. In this part, we actually have to add them. Oh, man. So here I'm going to have to add the 0.0. Let's see. So here I'm going to have to add 0.0099 to 0.0265 to 0.0828 to 0.2086 to 0.3146, and I get 0.6424 or 64.24%. And there's that one. Number 12. This is the one that I had trouble with. The first part says, what's the distribution? Now the average is 19.12. Well, that's easy. Which one is it? It's the one with the average of 19.12. So this is A. The next part says obtain a standardized version. So here's where we got to find what's called a z-score. And here's a new formula you'll need in your notes. So this will be the last thing, and we're almost done. So a z-score is what standardizes something. Do you remember when we talked about the heights of an Irishman versus the heights of an American person? Or the heights of a Japanese person versus the heights of an American? In Japan, they measure someone's height in meters. In America, we measure our height in feet and inches or inches. So what we need to do here is find a z-score. And a z-score is found by taking the observed value, reduce that by the mean. So if you think about that, if the observed value is 50 and the mean is 60, you get a negative answer, and that's okay. That just means it's below the mean. And then you divide that by the standard deviation. Okay, so that's how you calculate a z-score. So I'll leave that up there another minute. We'll go back to the exercise and we'll see what happens. Okay, so here we go. To find this z-score, it's the observed value x minus the average. So I'm thinking this is going to be c, right? Okay. The next part says, now what's the shape look like once we standardize it? Once we standardize it, remember what our mean is. Our mean is now 0. And now we're going to actually have to find z-scores for 17 and 18. So what I'm going to have to do is take 17 minus 19.12 and divide that by 1.42. And I get negative 1.49. I repeat that for 18. And I get negative 0.79. So the calculation there is 17 minus 19.12 all over 1.42. And then repeat that with 18, and then repeat. You got to group the numerator. If you're using a calculator like that, you want to group the numerator. So I'm going to repeat that for 22 for this last part, which is 2.03. And we're almost done. The last one, what's the graph look like? Well, the average would be in the middle, I would think. So around 25. So I'm thinking it's probably going to be this one or this one. Let's try A, see what happens. Okay. And then, is this normal? I would say yes. So that's it. It's been real. It's been fun. Does anybody have any last-second shout-outs? The future Mr. Minnick, whoever's covering my class, thank you. Whoever's watching back at home on YouTube. Mr. Baseball's pitch is weak. He's being called out by somebody. I'm not going to say who, but somebody's calling him out. Well, that's it. Have a great week. See ya.